Okay, how's everyone doing? Good. Wish I could say the same. I've been up since 4. I'm still struggling a bit with this particular class, but we'll try something a little different tonight. They do have some PowerPoints that walk us through the lessons. Um, so we're going to give that a try and see how that works. I've gone through them a couple times. I don't really like them either, but we'll see. It does help us focus on the important part. So I will bring out that. Uh, so regardless of what the syllabus says, you're responsible for learning the content and going through the homework portion of the lesson will do that. So if you can work through that. Also, I've been getting emails, and some of you have come and told me there's certain things like when you have to draw the line, you've got it in there correctly. And I checked a few of you. I checked your answer against what they say the answer is. It's the same thing, but it doesn't give you the points. I understand that. But so as long as you can get about 90-ish for a score, I'll give you the full points. So we'll do that, as long as you're making good. And I can't go through and check each one and say, oh, this is right. So if it's a big issue, I'll look at each individual one. But I think it's a small enough thing where there's a few things that you don't get points for. We'll get you all those points, but I don't want to go through and try to rectify all that. That'll take a lot of time. And I trust you. So, and that's the idea, is that you're working through it, and you're building that understanding. I also opened up something that was hidden, is a quiz. Now the word quiz might make you nervous, but don't. It's a ungraded quiz. But what it is, let's see, where is it? So quiz 2.1 to 2.3. You might want to take a look at that and see how that's going. The test will be somewhat based on those. So those are some questions to take a look at. Okay. What I will do is this weekend, I'll actually work through that in a video thing, and I'll post that probably Sunday. But if you can go through it on your own, um, see things that make sense. There's some multiple choice stuff in here. There's some fill in the blanks, but it's similar. I think it's 6 questions, 7. Oh, I guess I forgot how to count. It was something that was 6 questions, 11 questions. So it's kind of like a practice quiz. If you don't do it, that's fine too, but these are kind of there. I'm told that when we get closer to the exam, I'll get a copy of that, and there will also be a practice exam. So I'll have those for you. We'll shoot towards that. So homework, exams, and you're fine. If you take a look at the learning, what is that, the LN, the lesson, you can work through those if those are helpful, but those are kind of what we're going to do with the PowerPoint. They're similar type activities, except those in the lesson, they're more interactive. You can actually play with them. So I would suggest going through and maybe playing with a few of the interactive apps. You'll see them on the PowerPoint more as just static things, and then they're going to graph them. But that's what we'll use the lessons for. Okay. Bottom line is, if you can learn the material, we'll make it work. I'm not so much about due dates that you learn it today or tomorrow. I can always extend things. But the problem is if we go too far out, then there's a lot of work to do in 1 or 2 days, and that will blow us up. So try to keep on track, but I'm not going to, if you're a day or 2 behind, I'd rather extend and let you go through and earn those points and learn the lessons than not. So keep in touch with me that way. We'll make it all work. So there's the quiz. Any other questions? How are we coming with the textbook? I heard that some were picking it up from the bookstore, that they did have a supply. Yeah? Okay. And then, of course, there's the whole completely online way of getting it, and at least getting the access. So we'll do with that. Okay. So this is from the textbook itself, at least the instructor part of the textbook. I don't know if you have these PowerPoints or not. Again, they do lay out the lesson in the way that this system is designed to teach it. And I've gone through it, and it will teach us about the basic of, basically we're talking about slope. the slope of a line. But they do it in a context that helps you connect with what it really means. So some of this is going through and they're going to talk about units and stuff. And again, their goal is that you learn it uh, rather deeply so that you'll remember it. One of the things we do with math is most of you, how many of you have had a Algebra 2 class before? Most of you. How many of you have had a trig class before? Most of you. See, this is what we do in math. We teach you again and again. And I always say we obviously didn't do it right the first time because we have to teach it again. And that isn't your fault. It's our fault as educators, the way we're doing it. So this is an attempt to help you to learn it and sort of learn it for once and be able to apply it. But math is because of math is very abstract. And so what we're going to attempt to do today, and we'll see if we won't overdo it, but to be on track, the syllabus says we should be about at 2.6, which is right here. This is a shorter piece, and even it's a few slides, but the distance formula itself is pretty short to cover. This part is fairly short. So the big part of the lesson is 2.4. So we'll get through that, and we'll see if we can pick up 2.5 and 2.6. We'll be right on track where we're supposed to be. And then Thursday, we'll look at 2.7 and we'll start into chapter 3. All right. And no, I had it the right way. Also left part of my technology at home, so we are live streaming. So this is recorded. We'll see. Last time the Bluetooth cut out on me, so you saw the stuff I was doing on the board, but the sound was gone. Hopefully it all works out, and we'll do the best we can with what we've got going. Okay, so constant rate of change and proportionality. We're going to see these are kind of related. What does it mean to be proportional? Proportional. The ratio, good. So if I were to make this cup taller and I wanted to keep it proportional, what would I have to do with the diameter of the top? I make this taller, I'd have to proportionally make this bigger too, right? So that it would be similar, it would be bigger, but all the dimensions would be the same or in the same proportion, the ratio. Good. Constant rate of change, that's the idea is that if we're going to change one part, we change the other part in the same ratios and everything like that. Okay, so we're going to be looking at two quantities again. Again, with our math, we really always have two variables, an x and a y. Typically, we change the x, and that results in some kind of a mathematical change to the y. So they're two variables, but one's connected to the other in some form. So we change an x, and that causes a mathematical change in the y. And what we're going to see, what we're looking at is things that are a constant rate. So typically we're multiplying by some fixed constant. Okay, we want to make things twice as big, we multiply by 2. We want to make them half as big, we multiply by 0.5 or 1/2. Okay, so we've got what is this? This is a photographer, so we got a photo that's a 6x10, and we want to make it bigger, but we want to keep the ratios the same. So what if we made this new width? What if we made this 20? What would we have to make the new height? Perfect. Double the one, double the other. That's proportionality. Good. We're going to also look at some more complicated things. But so what is the ratio here between the height and the width? 6/10. We could 3/5, 0.6 if we want, right? So we could use all of those different forms. Sometimes some questions you switch it. You might say it's 10/6 if you want. That is saying the width to the height. So we can look at things in multiple ways, but most of this lesson is going to look at, let's change this and how does it affect this one. Um, so we're right on. So if we want to enlarge the width to 25, that wasn't as easy as 20, right? Because 20 we just doubled. But if we went 20 over here, what would the height have to be? 15? You guys are fast. Or is it in the book or something? No. 15, good. Because it's, again, 25 is 2.5 times bigger than 10. I guess is what you said. So if you take 6 times 2.5, you'll get 15. Good. So we can involve decimals and fractions and those things. See, everything's already printed up. It's kind of cool because it's less work for me, but it's harder to kind of explain things when everything's written out. So, again, that's just what we said. So it'll be there. 25 inches is 2.5 times bigger than 10. So we just multiply by 2.5, and we keep that ratio the same. Okay. So we've already talked about this. What ratio must remain constant to assure the photo is not distorted? We talked about it 6/10 or 3/5 or 0.6. We could use any of those ratios. They're all equivalent. And they're going to use the 0.6, just directly multiply by it. Okay. 6/10, though, we can think that as a ratio. So if we resize the photo, maybe made it smaller, the width was only 1 inch, what is the height going to be? 0.6, because 1 times 0.6, right? 2 inches, 2 times 0.6, 1.2. So it's this constant rate of change thing. 5 times 0.6 is 3. And then we've already done this one, but 25 times 0.6 also gives us to the 15. So we've got this idea of constant rate of change tied in with proportionality. Okay. So then we're going to construct a graph, plot some points, and show what's happening. So we're going to see the graph on the next one. So, we would put a point somewhere, and the one I would start with is, let's see if I can get my pen. I might start with this, when the width is 10, the height is 6. And then we calculated at 25 that it would have to be 15, so we could do that one. Then you could draw the line, and you could check each one of these other ones. We said that it's got a ratio of 3:5, and so if the width is 5, the height is 3. Yep, that's there. And I guess if we shrink it down to 0, the width is 0, the height is going to be 0 too, right? So we're going to see that this is for proportionality, we really need this line to pass through 0, 0. Okay. If it doesn't pass through 0, 0, then the proportionality is not there. The rates are the same, but there's like a different starting value. Okay. So, and again, we have to choose what our x is, and in this case, they've chosen the width to be the x, so that becomes our variable that we're going to play with. The other one is a resultant change. It does change, but there's a mathematics behind it, and we've seen just multiply by 0.6, and we get that. So far, doing good? Okay. So now we look at this, and we can define it with variables. X and Y were perfectly good variables, but we could also use other ones. We could use H and W, H for height, W for width. You see how that works? They fit the situation a little bit better. But then also, as we're going through the algebra, for me, it's a lot of times easier to think in terms of X and Y, because I get used X will be on the bottom, Y will be on the top, Y equals X with some math done to it. So just keeping track of, again, in this case, that the W is going to be our input variable. And so we can come up with a simple equation that the height is equal to whatever the width is times 0.6. And it sort of makes sense because the height is smaller than the width, so whatever the width is, the height's going to be a little bit less. So if the width is 10 times 0.6, we've got a height of 6. And when we have this kind of relationship, we're going to see that is proportional. We're also going to look at other linear equations where it doesn't go through 0, 0. It doesn't start at 0. There's some other value here. And we'll see that the rate may be constant, but it's not, the variables themselves are not proportional because you're not starting, they don't both start at the same place. Okay. And that's a kind of a concept that will come in. So the height of a resize photos is always how much times larger or as large as the width. 0.6. It's hard to think that way because it's actually smaller, so we don't think of it as being larger, but it's 0.6 larger. That means it's smaller. Okay, good. And again, we talked about that ratio coming from 6 to 10. And you can also switch it if you want. That's why sometimes we go with the H and the W as our variables. Makes it a little easier to say, well, let's talk about the height being the one we want to adjust to and make the width the variable. So we could also think of it as 10/6 and 5/3 if we want to talk about the ratio of the width to the height. So again, then we start changing the height and calculating the width. So we see where this reciprocal number comes in. Okay, so we can switch. So, you know, if you work on a problem, you might choose your X and Y differently than your neighbor. And what you'll see is that your rates of change will be reciprocals of each other. And they still both will work. So they can both be correct. Okay. And again, just bringing home the point as we increase the height, we've got to increase the width. But this time we could also focus on how much is changing here, right? So this is the change. What we've been calculating is the total, how much the total height is going from one to the other, but we might also look at the amount of change. And this is going to get us more closer to this idea of constant rate of change. Okay, and actually, I think it's going to come up next anyway, but we'll see that that ratio, in this case, 3 to 5, we had 3 to 5, we had 6 to 10, same type of deal, just a little bit smaller. We can see the same graph here, width of 10, height of 6, so we're talking the same thing, a width of 5, a height of 3, that this rate of change continues all the way along in here. So we've got a, and in case this one, I would go over 3. Notice you go up. So actually, if you go over 5, 1, 2, 3, 4, 5. Did I count that right? 1, 2, 3, 4. No, one more. 5. Then we should go up 3. 1, 2, 3. So a run of 5 should result in a rise of 3. Here we are on a slope, a rate of change, and we see constant rate of change because we want to keep things constant. Okay. So if we change by 2.5 inches in the width, make that 2.5, will it always result in a 1.5 change in the height? Well, because if we go by 5, we're going to go up 3. So if we went half of 5, which is 2.5, we should go half of 3, which is 1.5. The other way we could look at it is, as I've got drawn here, this ratio 1.5 divided by 2.5 gives us the value what? 0.6, 3 over 5, 6 over 10 if you want to, but yeah, 0.6 if you just divide it out. So it's all got the same, again, the constant rate of change. So uh, we can use any of these numbers to figure out how we're doing this change. But that only happens if we have a constant rate of change. And again, if we start at 0, 0, then this is called proportionality. If it was 3 times as if the width went by 3 times, what is the height going to have to change? Width is, so we start off, we know that the width, if the width changes by 5, the height changes by 3. To keep that same proportion, if the width changes by, where is it? 3, how much does the height need to change? It needs to change less than 3, right? Because we have to keep that at 0.6. Now the math is, how much? Well, 3 in the width, what is, how much more does the height need to be? It needs to be less than 3, probably 1 point something, 1.8. So 0.6 times 3 gives us 1.8. Okay, so whatever the change in the height is, if we're going to change it by 3, we need to change, sorry, if we change the width by 3, the height will have to change by the 0.6. So 3 times 0.6 gives us 1.5, or 1.8, sorry, 1.8. But it's not as easy as a ratio 5 to 3, 10 to 6, you know, so those are the even ones, but we can also get ones that are partial. Okay. Again, they like you to talk a lot, so we're going to move a little bit forward. So again, let's just think of this one. For any change in the resized photo's width, the change in the resized photo's height is always blank times as large. 0.6. Same number we answered before, but they just want to bring it home because it's a constant. Okay, constant rate of change. Okay, so now we're going to get away from the photo, try something a little different. We've got these cylinders. They're emptied and water is poured into the narrow cylinders up to the 11th mark. How high would this water rise if it were poured into the empty wide cylinder? Okay, so there are 2 cylinders, one wide and one narrow. Both cylinders have equally spaced marks for measurement. Water is poured into the wide cylinder up to the 4th mark, CA. This water rises to the 6th mark when poured in the narrow cylinder. So we know this is 4. If we poured it in here, it would come to 6. So what's our ratio that we're working with? 4 over 6, 2 to 3, 0.66666. Yeah, so we go with all of those. So now it's changing it. If we went to this narrow cylinder that came to the 11th, what's it going to come to on the wide? So one way to look at this is it's 4 to 6, right? Wide to narrow. And then you could, so is it going to be more or less than 11? Less, because it goes from the narrow, it's going to go to the wide. So we know it's going to be less. So this is one thing I always think about, because if I do it backwards, I get a bigger number. Oh, I should do by the reciprocal, right? So I multiply 11 times 0.666, or by 4/6, right? Another way, since it is proportional, we could cross multiply and then divide. But 4/6 is 0.66, so what is 11 times 0.66? 333, yeah, something. Now, it would have been nicer if they would have said it went to 12, right? Because 6 to 12, okay, then 4 goes to 8. That we can think about. So sometimes when you get a problem like this, you say, okay, let me think, oh yeah, 12, this would be 8, so this must be, since we're going to 11, a little bit less than 8, 7.33. So go for those you know, ways of checking whether you're going the right direction. Because what I find is, in my personal experience is, half the time I went the wrong direction. It just meant I multiplied or when I should have divided, or divided when I should have multiplied, got bigger when I should have got smaller, smaller when I got it bigger. But I was on the right track, right? And all I had to do is, if I would have done the check, I'd see, oh, I'm going the wrong direction. Let's just do the opposite. Boom, we're there. Okay. Good. Okay. And they break it down. They use 2 to 3 times 11, which would be 0.666 times 11. Same answer they got. Okay. And now what they're going to do is set up this proportion. So we can think of this again as a constant rate of change reduced, starting with, we knew that when this was at 4, this is at 6. So when the wide is at 2, the narrow one's going to be at 3. So it's giving us a ratio, a proportion between which one's the wide? The wide one versus the narrow one. Okay. And again, this is mathematically, I had to think, because bigger numbers actually for the narrow one, the smaller numbers for the wider one, because it's wider. Okay. So what does it mean? It's the ratio. It's the proportionality. It's a ratio between that we could go back and forth between the two. And again, if we know one of these, we're able to figure out the other by using a proportion. How many of you use cross multiply? I use it all the time. In fact, yeah, so if we know one of them, we can cross multiply and then divide. If we knew this one, we'd cross multiply this way and divide by 2. We got it. Okay. Or we just take the 2/3, make it 0.66. And but then again, we have to realize which one are we multiplying or are we dividing. So as long as you keep track of whether you should be getting bigger or smaller, then it'll become more intuitive. Okay, so now it is proportional. So if in the last one, we were actually talking about amount of markers. What are we talking about when we have this little delta here? Awesome. Just the change. So there could already be some liquid in there and we add some more. So we could be just measuring a change. We could also go from 0 to that, and just like that's really what we were doing last time. So it makes sense that the change of y over the change of x is 2/3, or we can start getting to an equation. We multiply both sides by x. So that's why if we know the value in the narrow, we just multiply it by 0.66, we'll get the amount in the wide. If we know the amount in the wide, what we have to multiply by is the reciprocal, 3/2, 1.5, and then we'll get the amount in the x. Let's see how that works. Okay. All just by knowing 2 pieces of information. What's the measure in this one? The same water measures this in the other, and now we can calculate for any amount filled in one how much we're going to get in the other. Okay, and now we can even calculate how much we need to change from one to get into the other. So we could start with some already in here, add some more liquid, and then we'll know how much we need to add to the other to make it equal. So we've got this thing. So when x is 3, what would y be? Think about it. When x is 4.5, what is the value of y? So what are we multiplying by? 2/3. This is the easier one. 2/3 times 3, right? It's going to be 2, because the 3's will cancel. 4.5 times 2/3, a little bit harder to do, but 9. I guess that 4.5 is 9, and then divide by 3 would be 3. Okay. So again, in each case, we just want to focus what we're going to. Once we know the constant rate of change, we're able to use that to calculate any given value. What if they gave us the y values? divide by 2/3 or multiply by 3/2, reciprocal, whichever is more convenient. So they give you those, and I wrote over the top. Okay, so I think we've got this one down. So this is the part where they bring home that when we're talking constant rate of change, as long as there is a 0, 0, we start at 0, one starts at 0, the other starts at 0, which, empty things, then we can call this, we can say y is proportional to x. Photograph, if a width is 0, the height's going to be 0. So as long as we start at 0, 0, then that's also called a proportional. If it doesn't start at 0, 0, then it is a constant rate of change, and we can still do it, but we're not starting at 0, so they're not directly proportional. The change is proportional. The change always will be proportional. But if we started, one starts with 5 in it or something, then we've got a y, on the graph we'd have a y-intercept, and the variables themselves are no longer directly proportional, but the change is always going to be proportional. Okay. Price of ground beef is $4.50 per pound. How would we express this as mathematically? If I buy in pounds, how would I 4.5 times in? Good. That's it. So each pound I buy is going to be $4.5, $4.50. So what would be a formula to represent the cost? C equals. Good. Perfect. Is this a proportion? Yes. If I buy 0 meat, I pay $0. So I got the 0, 0 there. So these are also going to be proportional. Okay. Construct a graph. Again, what we'd want to do is maybe put a couple points. I'd say 1 pound is $4.50. You could also use 0, 0. But the idea is that we start off with some value. So if I buy 1 pound, with this one it might be hard, but yeah, you could plot that as a point. Oh. You also might think, well, if I, oops, down here, 2 is going to be $9. 4 pounds, 4 times 4.5 is up here at $18. So again, we could plot them, and knowing that it's proportional, it's a constant rate of change, we could draw the line. Okay. And again, just thinking about it, if we want to switch the variables and we want the cost, because maybe we want to focus, I've only got so much money, for this much money, how much meat can I buy? Then we need to use the reciprocal. So instead of 4.5 times N, 1 over 4.5 times C. So we're dividing instead of multiplying. Okay. And those are two things that, they both work that way. And then they go ahead and try to get all the variables on one side. So this is the idea slope. Y is over the x. So have a slope of 4.5. You could change what you're calling the x and the y. And again, so it just, if we define the problem one way, we've got this, we're working with this. If we've defined the problem another way where C is our input, then we're using the reciprocal. But this is where N is the input, N is the x value, Y is the, C is the y value, this is that one. If we switch what we're calling x and y, N is the y value, C is the x value, then we've got to use the reciprocal. Okay. And what I find is oftentimes when you're setting things up, some of us have a tendency to go this way, some go that way. And it's not that one is right or wrong, it's just they're going to have a different order of the operation. One will be this and the other will be the reciprocal. So they can both work. It's just a matter of what the relationship is. Let's see, where are we? 25. So again, this is going to slowly go through, but it's going to build up for the next one. So we can see that regardless of what we've already purchased, if we start looking at what the change to buy additional is, if we want to buy another 1.5 pounds of hamburger, um, how's that going to affect the cost? The cost will change by what? 1.5 times 4.5, right? So whatever that change is, it's always the amount we're multiplying by is the same. Okay. So it's going to cost us $6.75 more to get 1.5 pounds more. Okay. So it's just showing us that it's proportional on amounts, but it's also proportional by just the change. And this is looking for justification. So why would it always provide the same increase in cost? Because it's proportional, right? Because the rate of change is constant. Okay. They're not changing the price, hopefully. Although sometimes with this economy, you think, if you take an extra minute to make your decision, maybe you're going to have to pay more, because it seemed that way with the gas for a while. You go in the morning and by afternoon, the prices were going up, weren't they? Fortunately, they come back down. But so that's right. They're proportional. The rates of change are constant. So we can always use, once we have that constant, that slope, that average rate of change, then we are able to use it. And no matter how much we change it, we just multiply it by 4.5, and that's how much the price will change. Okay. All right. I'm going to go through some of these a little quicker. Again, you can, okay, now we're onto a candle. So we'll do this because, again, we've played with some of the candles. You can go into the lesson, and they've got those applets. So a 19-inch candle is lit. The candle burns away at a constant rate of 2.5 inches per hour. Now, first of all, if we're talking it starts at 19 inches and it's burning down by 2.5 inches per hour, is this problem going to be a proportion? Doesn't start at 0. So I was kind of just throwing out, and that's right, because we start at 19-inch and we're going to go down to 0, so it's different. We've got a different starting value than 0. If it was a candle that would start at 0 and growing, then the growth would be proportional to the time. But since it's shrinking, it's actually, the variables themselves are not proportional. The change, it'll be negative. The changes will be proportional, but the values themselves are not. It's, what's that? We're still doing proportion, the change, but what we focus on here, only the change is proportional. And you're right, it's going to be negative because we're decreasing, right? We're losing, the candle's burning. So we show this, we start out at 19 inches. Every hour, 2.5 inches are burnt away, and so forth and so forth. And so we can come up with, though, a rate of change. So what is our rate of change? 2.5. And what's changing is the time, and as the time changes, the length, the height of the candle changes. It goes down by 2.5. Good. And so as long as we know how long it's been burning, multiply by 2.5. And what will we know? We'll know how much has been burnt, but then to calculate the new height of the candle, what do we need to do? Good. And that's going to be one of these next questions. So finding an expression, time times 2.5, and making it negative because we're losing it, and then we add the 19. I would think of it as 19 minus 2.5t. Both work, okay, because we're commutative, but something along these lines. Again, I would 19 minus, because that's what I think. This is the height, starting height, and then you subtract 2.5 times t for each hour, and you'll get directly to the height. This is why it's not, the two values themselves are not proportional because of that 19. But the change is always going to be proportional. Because to get the change, all we need is this. Okay. But to get the actual height, we always have to add back that 19. or subtract the change from the 19. Okay. So we could also talk about how much of the candle is remaining, the change in the amount of the remaining candle. And again, as we know, the change in time, every time we get a change of an hour, the remaining is going to be 2.5 less. So the change is proportional. The change in the remaining length of the candle is proportional to the change in the number of hours that it's burning. So those things are changing proportionally, but the values themselves are not proportional because we've got to go back to that 19. We get basically on a graph, we have a y-intercept. And when we see the graph, we'll see that. So it doesn't go through 0, 0. But the changes are always going to be proportional. How much time will it take for the candle's length to become 0? 19. How many 2.5s go into 19, right? Which gives us 7.6. Yeah, not an easy math to do in our heads, but exactly. We've got a 19. Every hour we're losing 2.5. We do the division. And again, we're able to do this because the change is proportional, the change is constant. And so it tells us that candle will burn for 7.6 hours from start to finish. Good. And we're going to, we've done enough with candles. Okay, here's a 17-inch candle. Again, we're going to do a constant rate of 1.8 inches per hour. A little bit slower burning, I guess. What does a negative 1.8 represent? What are the units on the negative 1.8? So time is involved, and what else is involved? Are you length, height? So inches per hour, right? So time and a length. And the fact that it's negative means it's decreasing. Very good. Constant rate of change, and we're decreasing by 1.8 inches every hour. Okay, so again, putting units on there. And so we see the constant rate times time will get us what? The amount that has been burnt in that time, right? So it's showing it as a positive value, so that's the amount we've lost. Then we would subtract that from what we started with to get the total. But we got, again, when we have change, we have two different, just like, the lady walking to her car, we could measure her distance from the house, or we could measure how much was left to the car. So there's oftentimes more than one variable that we can consider. So the candle, we could think about how much was burnt, or we could think about the resulting height. So when we give this, we make the rate negative. It's getting us how much was burnt. We're subtracting it from the original. So the whole statement together gives us the actual remaining height of the candle after it's burnt for T hours. Okay. So what it's helping you to see is the different portions of a math equation or formula. We talked just about this part. It's giving us how much is being burnt. We subtract it from the total, then the result is how much is left. All right. So as a change in the length, let's see, L represents the remaining length of the candle. Is that proportional to the amount of time it's been burnt? Change to change. Right? Remember, with a constant rate, as long as we're talking the change, those are always proportional, even though the two variables themselves are not proportional because we didn't start at 0, 0. The change will always be proportional. Okay, so we get a slope of negative 1.8. Is L proportional to T? We've already answered that one. It didn't start at 0, 0, so it's not. The variables themselves are not proportional, but the change is. Okay, let's now get into 2.5. So that's constant rate of change. And what we're going to see is it's very much related to this concept of average speed. Okay, average speed does not mean that you're going the same speed all the time, but it means that from this point to this point, we get the average. Okay, and we're going to look at a couple instances where the actual rate of change is not constant, but we can apply this, what we've been doing. Well, if it was constant, this is what it would need to be. Okay, and so we'll see that average speed is really thinking of things as terms of being a constant rate of change. So, policeman is positioned on a road, side road without a radar gun, doesn't have a radar gun. Is it possible for the police officer to determine the speed of a car? And if so, how would they do it? Perfect. Just like we did with Usain Bolt, right? That little thing of there, yeah. And actually, they can use the dashed lines. That's part of the reason the lines are dashed, because those from the airplane they can measure the time between those dashes somehow. At least that's what my dad tells me. But be careful. I did this once to try to show a judge. I had a ticket, a camera ticket. I had the picture when I started and ended, and I did the math on it, and they didn't have the accuracy. The problem was is the judge didn't understand my math. I should have, brought it down, so I still had to pay the ticket. I was speeding, so I didn't feel so bad. I was, but I thought, hey, this piece of data, I can show them. I'll use this stuff I use here. I'll show that my speed could have been 20, or it could have been 45, but the data doesn't prove it. Well, I lost the judge on that. So she says, I got my degree a long time ago, and I'm sorry, I'm not following your math, and it's going to cost you. You're going to have to pay your fine. So, but you get a starting place, an ending place, and the time in between. Um, so that's basically it. So, yeah, and even if the thing is with that, we're not getting an instantaneous rate of change, which is kind of what's on your speedometer, right? They might change speed in between, but we are getting an average rate of change from start to finish. Now, what about a radar gun? How does a radar gun work? Actually, it doesn't, because the only way you can calculate speed is to have a starting and a stop. It just does it so fast that it looks like it's instantaneous, but it's really measuring two places, and then it's got a timer in there, and it does it so quickly we think it's instantaneous, but it really isn't. It's like a 0.5 second. It's a millisecond, but so we would call that in the real world instantaneous. But even a radar gun is taking an average between two readings. Just does it very quickly. Okay, so but bottom line is, and that's what it's basically saying, is we're not really getting instantaneous rate of change. We're close enough, but we're getting an average rate. Okay, so we're going to look at a couple examples here, and we're going to be given an equation. So we've got a formula. A car is driving away from a crosswalk. The distance d in feet of the car north of the crosswalk is t seconds since the car started moving, given by this formula. So time is getting squared. What does this 3.5 mean? Constant what? What does it mean in this case? It's the initial. If time was 0, it means the car was 3.5 from the north of the crosswalk or wherever we are, right? So if we go from 1 second to 3 seconds, these values are what kind of values? Or which variable are those representing? time. So we can put them in here. And if we do that, what can we calculate? The change in time and the time at those each of those seconds, and then the change. Right. So that's what we're going to want to do is when we're at 1 second, we plug in 1 second. 1 second squared is 1 plus 3.5. So the distance at 1 second, right, is going to be 4.5. What will be the distance after 3 seconds? So that's 9, 12.5. And this writing thing is not so good, but it'll all give it to us. So then how would we find the rate of change, average rate of change? Subtract the distances, subtract the times. It's 3 minus 1 is 2. So after 2 seconds, how much does it change? Those distances, we subtract them, what we get? 8. 8 divided by 2, 4 feet per second, right? 4 feet per second. So the distance from the crosswalk is 8 feet. The change in distance is 8 feet, right? So that's what we're calculating here is the change. The actual distance is now 12.5 at 3 seconds. After, when 3 seconds, it would plug that in. That gives you the actual distance. But the change in distance is 8 feet. Okay, so now we're going to graph this, and they show us what the car, does this look like the car is traveling at a constant rate of speed? No, it's speeding up. It's going away. So, and that's why you get this kind of a curve. But what we're calculating is if it were going constant, there's 4 feet per second, right? So I'm going to wait till it draws it for us. There it is. So thinking of if this, was a rate of change that was constant, then what we're really calculating, I thought here it is. They're going to draw what we're calculating with average rate of change is what would the constant rate of change need to get the same thing done. Okay. So it would have needed to be this constant rate to do the same thing of this speeding up. So, this second half was faster than the first half, but if they did it at a constant rate, that's what we're calculating. And again, in the real world, that's mostly what we do is we can spot it's here and then it's there and how much time has passed. We can get an average rate of change. And even a radar gun is getting an average rate, it just does it much faster. Okay, so that's all the mathematics of change. So if you got a photo and you know how much time elapsed from the two, you can do the math, but you got to be able to teach the math to the judge to be able to get off on the ticket. So, okay, so we call that the slope of the line. And we're going to be doing this with other functions. A lot of times we're calculating the average rate of change. In fact, when you get to calculus, that's really what calculus is about, is calculating this average rate of change. Bless you. But what we do in calculus, we use a few more tools. We move the points so that you're getting the average rate of change really so close together that you're getting an instantaneous rate of change. Okay, so that's the tools we're working you towards as you go towards calculus, bringing the 2 points together and getting instantaneous rate of change. That's the tools of calculus. Tools of algebra, we get average rate of change. It's the best we can do. Okay. All right. Let's. We're almost there. There's a lot of questions, but I think we're doing pretty good. Okay. So what would we do? Sort of same setup. What if we wanted to calculate the average rate of change from t equals 3 to t equals 4.5 seconds? Will it be the same as what we already calculated? No, because the speed is changing. So if you change the time intervals, the average rate of change is also going to change. So that's good. So it's when we, a lot of our questions are set up for constant rate of change, but in the real world, very few things are constant over a long period of time. So we've actually got to recalculate it. Now the t equals 3, we already calculated that that would be 12.5. That didn't change. But now we need to recalculate what's going to happen when t is 4.5. Plug that in, and what do we get? And I think that's, 4.5 squared. Probably need a calculator. How much? 22.75, and we're getting to 23. Very good. So I'll click here, and it'll give us 23.75. So we're getting where we need to use kind of paper and pencil calculators. But we do the same process. We can subtract those. The time is 1.5 seconds, right? 3 to 4.5. So again, calculators would be helpful, but we get that at that point, it's 7.5 feet per second. Sounds like from 3 to 4 feet, 3 to 4.5, they've slowed down from what they were going from 1 to 3. So I guess 1 to 3, they went faster. They were 8, average of 8. And then from 3 to 4.5, they're now only going an average of 7.5 feet per second. Must be slowing down. Okay. So again, we talked about all of that constant rate of change and how it's proportional, and that the change is the change, and it does, it's always proportional. But when we don't have constant rate of change, such in something that's moving, we've got to recalculate that average rate of change for any interval, because it will be different. And if we went from 1 to 4.5, that would be a different rate of change than any of these. Okay, they might be all kind of close. I imagine if we went from 1 to 4.5, it would be probably somewhere between 7.5 and 8, right? Because they were going faster and then they went slower. So it should probably still be in that ballpark, but it would be different. Okay, we're going to skip over this one. This is just giving us, again, more practice with a more complicated formula, but the same type of thing. Plug in the time, you can get the distance, subtract the time, subtract the distance, divide, and you can get the average rate of change. Okay, and distance changing. And so this is what we're getting towards. Average rate of change also is really just the slope formula. So we've got a change in the y's in the top, change in the x's in the bottom, and then we could throw our units on there, feet per second in this case, and that gives us our slope, our what we often use as a constant rate of change when we talk of linear functions. So sometimes we use this to approximate, okay, from this time to this time, here's our average rate of change. Let's just pretend it was constant because that's easier to calculate, and that's what we'll use, okay? So at least on those parameters, from 1 second to 5 seconds, or 5 seconds, between 2 to 5 seconds, right? This is traveling at 6 feet per second. Okay, average rate of change, slope. We go till how long? 7:15 or 7:10? Okay, we'll make it. Oh, let me back up. So this would be, if you saw this graph, what can you tell me about what this car is doing? Decreasing and then increasing. Now, this is a number of seconds since the car started moving. And this is distance in feet from the intersection. Okay, so this is a directional change, right? So it's driving towards the intersection at this first part and then going away. And the rates are changing all the way along the way. And you'll see that where it changes direction, it's, if we calculate the rate of change here, we could almost get a zero, a horizontal, right? There's places where, and if you're going to change direction, it's kind of wise to do that, slow way down and change your direction. And yeah, the speeds are, since it's going, the orientation of this, we're going to get a negative rate of change, right? Because we're coming towards it, and we're going to get a positive rate of change here. and probably as it goes away. Okay. Um, South of the intersection varies over the first 5 seconds as it started moving. So we can see where did it change. Changed at 2 seconds. So for the first 2 seconds, it was getting closer to the um, sidewalk or crosswalk, and then it goes away. Okay. So if we go from t equals 2 seconds to t equals 5 seconds, right, we're going to get this average rate of change from 2 to 5, which gives us what? The average rate of change gives us what would the constant rate of change need to be to get the same distance in the same time. Okay, so here it was slow and then speeding up. Here is if it were just to be a constant rate. Okay, so average rate of change is what constant rate of change is needed to accomplish the same thing, where in this case, again, we're getting a variable speed. The constant rate of change? The constant, there is really no constant rate of change. What it is it's when we're getting an average rate of change, and the meaning of that average rate of change is what constant speed would be needed to get there. Although in our situation there is no constant, so that good point to bring that back. There is no constant rate of change. It's an average rate of change, but we think about that average rate is what would be needed if. Thank you. Yes, it's the constant rate of speed needed to do what this was doing, and that's what it says there. So the constant speed another car would need to travel in order to cover the same distance in the same amount of time using constant rate of change. Okay. And again, if we went from 5 to 11, we could do the same calculations. And what we see is if we go from 5 to 11, we end up covering 90 feet. And again, what we get to that the average rate of change, we don't have a constant going on because we've got a function that's varying the speed all the way along here. But what we can calculate is average rates, and we use that with the slope formula. Okay. And that's what, like at accident scenes, that's what they look when the brakes were put on, and then when did the car stop? That's what they use to, in this distance, they can kind of measure time. They can measure the length of the skid marks if it's, if the conditions are right, and then they could say, well, for that kind of a car, the weight, it should have, if it's this long, then it must have been going this fast. So there's various ways they can do it, but again, as long as we know the start point and the end point, we can always get an average rate of change. Okay. So what's interesting is that, again, when we have this, we go back to this other formula, the distance is t squared minus 2. What we're going to do is we're going to go through this, and we're going to see that as we calculate it for different intervals, from 2 to 6, 6 to 10, 10 to 11, the average speed is actually going to change. Again, you could plug those in, do the math behind it, but from 2 to 6, we end up with 6 feet per second. We are speeding up from 6 to 10, right? Because that gives us 14 feet per second. And it's a 4-second interval. Plug those in and you get your Y values. But you see that the rate of the speed is not constant anywhere here. It's changing. And, this last one going pretty fast, I guess, so it's this object is picking up speed. And so what would you say if we went from 2 to 11? So what if we calculated from 2 directly to 11? What kind of a number are we going to get? How much? 13 might be good. Yeah, somewhere in between here, we know it's picking up speed, so probably more than this, but less than this, because we're, you did that in your, could be. Let's see. Well, since this average speed is increasing, we should expect, well, they don't give us the answer, so I'll leave it up to you, but yeah, it would be somewhere in between those two endpoints, right? Because we're picking up speed. Yes. Well, it'd be 9 seconds, but then you have to get the distance, the change in the distance. So the time changes by 9 seconds, um, and then it would just depend upon what we end up with a change for the distance. We divide those two, and yeah, 9 is good point, maybe 13 somewhere, but certainly between 6 and 19 feet per second would be a good average. And again, this is the same thing. Uh, we see a process that 1 to 5 seconds is 4 feet, 3 to 5 is 6 feet, 4.5 is, so this is something that in the end is going faster than the overall average, right? So it was slower at the beginning, and it's successively picking up speed, getting faster. Those average rates of change are changing um, over different intervals of time. Okay, and again, you could calculate it by getting the distance, the change in the distance. We certainly can do the change of seconds of time pretty quickly. So 5 minus 1, this will be 4. This will be 2 seconds. This is 0.5 seconds. But we need that distance. How much is the distance changing? And that's how we get these. Okay. So what I'm going to do, we're close enough. There's not quite enough time to do 2.6. It's kind of brief. We'll bring that together on Thursday. We'll do 2.6, 2.7, and potentially get into 3.1. Um, Good. Thank you.